So this is Lecture 2C, welcome. And title is Non-Existence of a Limit. In Lecture 2B, we looked at examples where we could apply techniques to check if the limit exists. In this case, we're going to apply techniques which we can use to determine if the limit does not exist. There's some guesswork involved because you have to assume one or the other, determine which approach to take. Clearly, if you fail at one, it's probably the other. So again, this material is from chapter 15.2 of the text. And the objectives here are determining the non-existence of limit for a multivariable function and illustrate the method used to determine if the limit does not exist for two variable problems. And so we're going to be focusing on the two-path test, which is basically a contrapositive proof. All right, so the outline, again, as usual, this is just different slides that you'll be seeing. I will just skip over it. It's just for handy reference, that's all. All right, so just some general guidelines in terms of if we assume that the limit does not exist. First of all, simplify the functional expression so that the resultant expression consists of polynomials or well-known functions for which it is possible to show that a limit does not exist using the two-path test. So we like to try to precondition things as much as possible before we actually apply the limit test. All right, so again, just to recall the two-path test, what is it? Well, all we need to do is prove that for at least two different paths in the xy plane, approaching the boundary point, open or closed set, you get a different limit. So you don't only have to prove, just pick any two to show that you get a different limit, in which case you know that limit does not exist. Okay, so there are essentially two different techniques, both of them involving change of variables to implement two-path test. So one of them is more or less exactly the same as what we did when we tried to prove that a limit did exist, where we just assume that x is a function of two new variables uv and y is also a function of two new variables, the same two new variables u and v. All right, you make the choice based on the nature of the function. Secondly, you could also choose y equals m times x to the power of n, or x equals m times y to the power of n. M basically is going to indicate the slope, right? So if it was y equals mx, then m would basically tell you the slope of a line. If y equals mx squared, that would be a parabola, and m would basically tell you whether or not the parabola is opening quickly or opening slowly. But either way, it's a path. It's just not a straight line to the point of interest. So the choice of n is made by the user. M is typically set to a constant value and represents a particular path. Change the value m, you're choosing a different path. So the objective is choose functions for approach 1 or 2 that lead to an expression that allows you to find at least two paths for which the limits are different. U or v for approach 1, m for approach 2. So in approach 1, basically, once you make the substitution, you'll find the limit depends on the new variable. And as I said, the most common two-variable transformation, if you see an expression that involves x squared plus y squared, and the boundary point at 0, 0 is x equals v cos u, y equals v sine u, and it's understood that v is greater than or equal to 0, and u ranges between 0 and 2 pi. And again, if the boundary point is at 0, 0. Again, the mapping should be 1 to 1. You basically, for every x point xy, you have only one unique point uv in terms of a mapping. And in approach 2, z is some function of x, m, x to n, and ultimately what you're hoping for in most of the cases is that the final function reduces to a single function of m, which means that given that m determines a path, a function will have different values, which means for a different path, the limit will be different. So therefore, the limit does not exist. You can also do it the other way around, where you make a substitution for x, and basically the same apply. Again, these are functions that are typically used if we're looking at boundary points at 0, 0. You'll have to modify them ever so slightly if you want to apply something similar to some functions which look a little bit different. Okay, so example 1, let's take this function here, which is the limit of xy 0, 0, x plus y squared divided by x squared plus y squared. Clearly 0, 0 is a boundary point for the domain because the denominator becomes 0. So again, we're going to be using in this case the substitution of variables x equals v cos u and y equals v sine u. The limits on v are v greater than or equal to 0, and limits on u are between 0 and 2 pi. All right, so we have to transform xy coordinates into vu coordinates. So the point 0, 0 is equivalent to the point vu 0u. So v basically would be take on the value 0. Okay, so we now basically make the substitutions for x and y into the original expression, which is essentially what you see here. And then simplifying, you find that the v squared divides out and you're left with this expression here. Now that's a rational function, which means the limit exists. And v, of course, goes to 0, but in this case, v's not there. However, the limit basically will depend on the value of u. And what is u? Well, u basically is just this angle. So if I change this angle, that means this radial line is pointing in a different direction. So if I basically come down this path, approach 0, I get one value. If I move this over here, so it's in this direction, redo this calculation, I get a different value. Hence, the limit does not exist. All right, so let's look at the same function, but using approach 2. So here, basically, the easiest thing to do is to check the order of the numerator and the denominator. You'll notice here there's a square and a square. They're equal. And here, you're going to end up with x squareds and y squareds and xy, so also equal. So the simplest thing would be to just choose y to be equal to mx, where m will represent the slope of the line. You change the value of m, and then you'll change the value of the slope of the line in the xy plane. So we just make the substitution for y, which is here. And then after some simplification, we end up with 1 plus m squared divided by 1 plus m squared. Clearly, if you choose different values of m, the limit will be different, and therefore the limit does not exist. All right, so if we're to draw this on a diagram, which is what you see down here, you can see that for m equals 1, you have a line, right, in the first quadrant. For m equals 0, it's along the x-axis. M equals minus 1, basically, it would be in the second quadrant and the fourth quadrant. And so these are just different paths, all basically finally ending up at the point 0, 0. If we were to graph this particular curve, then this function, this is what we would see. And you can see this is the level curve for z equals 2. And this is the level curve for z equals 0. Okay, so it's clear that the limits will differ depending on the path that was chosen. So here's an interactive module where you can choose different values of m, basically different paths, which then take you to the point. Here, basically, this would be an example for this, m equals 1. Substitute in here, and you'll end up with a value 2. You can choose any values from m equals minus 2 to 2, just to show what the result will be. Okay, let's take another example. This one's a little trick here, but nevertheless, it sort of end up being showing that the limit does not exist. So you're given a function x squared y squared divided by x squared y squared minus x minus y squared. And clearly, if you substitute values of x equals 0, y equals 0 into the denominator, you'll end up with 0. So that means 0, 0 is a boundary point for the domain. All right, so here you might say, oh, we have a problem because, okay, this looks the same and this looks the same, but this does not look the same. This is going to have an x squared. This is going to have a fourth power. But let's try it. Again, everything is based on trying. If it doesn't work, then you try something else. So we're going to let y equals mx. All right, and we put it in there. So this becomes mx squared. The mx squared goes here, and the mx goes here. And then basically just through simplification, right, we finally end up with this expression here. And so what we're looking at is different values of m. So for instance, if we say that m is not equal to 1, okay, right, and x has to go to 0, I mean, as x goes to 0, y goes to 0, which is the same as this. So if x goes to 0, what happens to this term here? This is m not equal to 1. Well, this term basically becomes, this whole term here basically becomes vanishingly small and approaches 0. Let's take the other case. So this is for m not equal to 1. Let's take m equals 1. If you put m equals 1, then this is going to be 0. So this whole x minus 2 term has disappeared, and you're left with m squared over m squared, which means the final result for the limit is equal to 1. Well, here you have basically, for one particular path only, the limit is 1. For all other paths, the limit is 0. Hence, we can say the limit does not exist. Okay? So just, if you find that the limit along all lines is equal, this is just a warning, you cannot conclude that the limit exists. Instead, you should try along other curves if you suspect the limit doesn't exist. So this is all about skill and experience. Again, we have to give you problems which are doable. There will be functions for which it would be next to impossible to do the calculation, in which case you most likely will resort to the use of the delta epsilon method, even that might give you some problems. Okay, so the last example 3 is this one involving absolute value, which is a bit of a tricky function, but there's a simple way to deal with it. So we want to look at the limit as xy approaches 0 for absolute value xy divided by xy. Clearly, the point 0, 0 is a boundary point for the domain. Now, a little trick that you can employ is basically to take the absolute value and represent it in the form of an analytical function. So if you take the square root of xy squared, and take the square root, you end up with xy. However, the square root can only be positive. So in fact, the square root of xy squared is equivalent to the absolute value of xy. It's a very simple trick, and so you'll find this is a very easy way to work with anything involving absolute values. So you'll notice that the order of the numerator and denominator are more or less the same, or they are the same. So let's choose y equals mx in this case. So if we choose y equals mx and simplify, we find that we end up basically with this expression here. The square root of x to the 4th is x squared. It's always going to be positive. The x squareds cancel. But the square root of m squared is the absolute value of m. So this becomes absolute value m over m. That is the limit as xy approaches 0, 0. So consider the paths for m equals 1 and m equals minus 1. So the limit in the former case is 1, the latter case is minus 1. Therefore, the limits are different and means that the limit does not exist. So that concludes lecture 2C. Thank you very much for listening to the lecture.